All right, we've been talking about the XYZ coordinate system. Now we're going to talk about the NTB coordinate system. But recall in the XY coordinate system, the velocity is going to be tangent to the path. Say this is a path in XY space. If it's tangent to the path, there will be a component in the X direction and a component in the Y direction. The NTB coordinate system will be most useful when the velocity, acceleration, or the change in position would be defined in terms of X and Y. However, if the velocity and acceleration may be defined in terms of the path, then the NTB coordinate system might be helpful. So again, let's talk about a velocity that is tangent to the path. What we're going to define is a coordinate system such that the tangential direction goes in the tangential direction of the velocity, and the normal direction will be perpendicular to the particle, pointing in toward the center of the radius of curvature. This will be the normal direction. Now this coordinate system travels along with the particle, so it's not a fixed point in space, even though the path may be fixed in space, but the reference system travels along with the particle such that when it gets to a new spot, it's going to have a reference system that is, again, going instantaneously along with the particle, so that the tangential direction will go in the direction of motion, and the normal direction, the normal coordinate, will go toward the center of the radius of the path, of the curvature of the path. All right, let's talk about the change in position, the velocity. As you would recall, if you have two velocity vectors and over a particular time, they may move in this direction. And so let's call the change in position along the path S, and we're going to call the average speed is going to be equal to delta S over delta T. And if you recall, and again that velocity is going to be the instantaneous velocity, and so V tangential is going to be equal to ds dt, which will be the which is actually V magnitude. It's not the direction we talked about last time. All right, so V tangential is going to be equal to ds dt, which is equal to S dot. All right, how about in the normal direction? In the normal direction, let's call our velocity vector something that looks like this, which would mean that it would have a tangential velocity and a normal velocity. Well, V tangential and V normal. If the particle has a direction like this, if it's moving up like that, you can clearly see that it's moving away from the path. And that's against our rules. We will never have the particle moving away from the path. So we can suggest that V tangential is always a legal thing. In fact, it is always tangential, and V normal is going to be equal to 0. All right. So don't forget V normal is always equal to 0. All right. How about acceleration? So we've talked about tangential velocity is S dot. The normal velocity is going to be 0. The acceleration would look something like this. Let's say that at time 1 we have a V going in this direction. And let's say that at time 2 we have a different V going in that direction. All right. How about, again, I've kind of drawn these things like this, but V2, if V2 is greater than V1, we could say that it is accelerating, it is getting bigger as it goes around the corner, so that A tangential is equal to delta V over delta T, and A tangential, and that would be the average acceleration in the tangential direction. And if we want to look at the instantaneous velocity, or excuse me, instantaneous acceleration as A tan goes, or as delta T goes to 0, A tan instantaneous is going to be equal to dV dt, or equal to V dot, which is equal to S double dot. Very similar to what we've done before in rectilinear motion. In fact, the rectilinear motion, these are the rectilinear motion equations that apply along the tangential axis. And so if this equation applies and this equation applies, therefore ADS is equal to V dV also applies in the tangential direction for acceleration. How about in the normal direction? In the normal direction, let's say that we have some velocity vectors going in this direction, and this is at different times along the way. What we said before is that there is a change in velocity even though the magnitude may be the same. So we can say that there are going to be normal pieces of acceleration, normal components of acceleration going in this way. And so A normal is equal to V squared over rho. Alright, so those are our 4 equations that we'll be looking at. I guess 5 if you count this one, but we're going to say that the tangential velocity is equal to ds dt. The normal velocity is always 0. The atangential acceleration is going to be v dot or s double dot. AdS equals v dv counts, and in the normal direction we have v squared over rho. Now what is rho? Rho is the instantaneous radius. At any point along a curve, if the curve is defined as a function of x, there will be a radius that changes as you go at different places on the curve, and we're going to discover that on the next page here. Alright, so if the path is defined as a function of x, here's a path right here. At any point, the instantaneous radius can be defined by this that you may have discovered from your calculus books. Is that, again, if y is a function of x, we can take the derivative of that, dy dx, and then we can take the second derivative, d squared y dx squared, put it into this formula, and we can find out what rho is. And we're going to use this formula as we go along. If you need to know the length of the path from the formula, you may remember from calculus books and also from statics that we can calculate the length of the line or the length of the displacement along the path by this formula. Now, if the path is circular, just going around in a circle, and this happens pretty frequently, we can know that the path length is r, or rho theta, where theta is in radians, and we can find the length of the path very easily there. So if it's a circular path, rho is equals to constant, which is equal to r. Alright, so then just to sum up again, these are the equations that make sense in the NTB coordinate system. Tangential velocity, tangential acceleration, and normal velocity, or normal acceleration, and normal velocity is equal to 0. Now the last thing I just want you to recognize, and we'll use this, is that if the tangential acceleration is a constant, then the constant acceleration equations apply. And those are the ones that we developed in rectilinear motion, and we'll use those as we need to. Alright, so let's do a couple of little problems for you and see where we go from here. Alright, let's say that this boat is traveling around the circular path with a speed of 0.0625 t squared meters per second. We want to find its acceleration when t is equal to 10 seconds. Alright, first of all, by looking at the v is equal to 0.065 t squared, the first question we would ask, is it speeding up or slowing down? Well, as t gets bigger, velocity gets bigger, so I think we can conclude that it definitely is increasing in speed. And when we do that, we can draw a little acceleration vector, and we can say that a tan is going in that direction. Okay. All right. Now let's talk about how to get where we need to go. If v is equal to 0.0625 t squared, our tangential acceleration, well, let's find out what our velocity is at t is equal to 10 seconds. So at t equals 10 seconds, velocity, plugging that into there, is equal to 6.25 meters per second. All right, so that's an intermediate answer we'll need to keep track of. Along the path, we got our tangential acceleration, so a tan is equal to dv dt. All right, that's dt, and we can take the derivative, since velocity is a function of time. That's equal to 0.0625 times 2t. And evaluating that at t is equal to 10 seconds, and that's equal to a 1.25 meters per second squared, a tan. Alright, so that's a piece that we'll need to know. Now in the normal direction, a normal is equal to v squared over rho, and we solved this for v, so I'm going to put 6.25 and the quantity squared divided by our rho. In this case, rho is 40 meters, which is a fixed length. It's going around in a circle, so that'll be 40. That's equal to 0.9766 meters per second squared. Now, here's a little bit of dynamic speak. When it says determine the acceleration, it's not talking about one of the components. It's talking about the magnitude of the acceleration. So we have to say that A is equal to A mag, which is equal to the square root of those two components. So that would be A tan squared plus A normal squared, and we put those into our equation and we get 1.586 meters per second squared. That's our magnitude of the acceleration. Now if we draw the velocity, or excuse me, the acceleration vectors on our picture, we know that the normal acceleration direction is going in, so that is going like this, and we already calculated that it was speeding up. So here is our actual acceleration vector. Goes the square root of the sum of the squares and it goes into that direction, so A is in that direction, like that. Alright, let's do one just a little bit weirder. Let's do this guy. This guy's traveling around a speed of 300 over s. Alright, 300 over s. Determine the magnitude of the acceleration when t is equal to 3 seconds if it starts at s equals 0 at t equals 0. Alright. Alright, so what do we do here? V is equal to 300 over s. Again, is it speeding up or slowing down? Well, if it starts here and it's going in this direction, as s gets bigger, it's in the denominator, so velocity gets smaller, so therefore it is slowing down. And when we know that, we know that the tangential acceleration is going opposite of our positive direction. Our positive direction of the tangential axis is going in the direction of motion. However, the tangential acceleration is going in this direction, a tangential. Alright? Alright, let's try manipulating some equations and see if we can get there. We know that velocity is equal to ds dt. Velocity is determined as a function of x, so I can rearrange this and put dt is equal to ds over v, which is equal to ds over v. It'd be 300 over s, which is equal to s ds over 300. That's equal to dt. And we can integrate both sides of that. And I can bring the 300 over there if I wish. So let's do that over here. I'm going to say that from 0 to t, 300 dt equals the integral of s ds. Now s started at 0, so again that's handy, and we'll just put s like that. Okay, when I integrate this, I can see that this is 300t is equal to 1/2 s squared. And evaluating that at t is equal to 3 seconds, and I can get s is equal to 42.426. Alright, so that gets my s. Did that get me anywhere? I need to look for my acceleration. So let's go back to here and see if I can find, solving for s didn't really help me anything. So let me solve this for s as a function of time and see what I get. So if I do that, s is equal to 600 t, bringing that 2 times that, 600t, and I take the square root of that to the 1/2. Now I've got s as a function of time. I think now I can do something a little bit with that. That's equal to 24.49 t, I beg your pardon, t to the 1/2. Now, knowing that v is equal to ds dt, now I can take the derivative of that. That's equal to 24.49 times 1/2 times t to the minus 1/2, which is equal to 12.247 t to the minus 1/2. And a tangential is equal to dv dt, which is equal to 12.247 times minus 1/2 times t to the minus 3/2. Okay. Now evaluating that at t is equal to 3 seconds, I can get a tangential is equal to minus 1.178 meters per second squared. And again, it is negative, which corresponds well with our intuition here. By guessing that it was slowing down, we can see that it is going backwards. All right, so that gives us one piece of our acceleration vector. How about in the normal direction? A normal is equal to v squared over rho. V, did I solve that for v? I guess I didn't. So at t is equal to 3 seconds, if I plug that into there, I can get v is equal to 7.071 meters per second. And plugging that into here, our normal direction, I'm going to say that that is 7.071 squared over rho, and rho is given in the picture as 100, so our normal direction would be equal to 0.50 meters per second squared equals a normal. Now if I need to find the magnitude, that's what it was looking for, determine the magnitude. Alright, so we'll keep on going here then. A mag is going to be equal to the square root of 0.50 squared plus negative 1.178 squared, and that's equal to 1.2802 meters per second squared. And that's the answer we're looking for. All right, let's do one more. Oh, let's complete our picture here. So we have our acceleration vector going this way, and then the normal vector is a little bit smaller. The magnitude of this is magnitude of this one is 1.178. Magnitude of this one is 0.5. So our acceleration kind of looks like that. All right, looks like my pen's drying up here. That would be what the acceleration looks like. Okay. All right, let's do one more kind of easy one. Here's a little roller coaster, maybe something that makes a little more sense, I don't know. But let's say that the velocity along the path, the roller coaster starts at A and moves down to B, and the velocity along the path is going to be defined as 3t plus 17.5 meters per second. Starts at A and after 2.5 seconds arrives at B. Let's find the acceleration at B. All right, let's find the acceleration. Let's find, the velocity at B first. So he starts along the path, starts at A. So V at 2.5 seconds is going to be equal to 3 times 2.5 plus 17.5. That's equal to 25 meters per second. About the acceleration tangential, A tan is going to be equal to dv dt, and v is a function of time, so that's going to be equal to 3 meters per second squared. Okay. All right. Our equations that we need to plug things into are A normal is equal to v squared over rho. I've got a tangential acceleration, so the normal acceleration I need to find, I've got my velocity, so I need to find rho. How do I find rho? Well, rho, again the equation is equal to 1 plus dy dx quantity squared raised to the 3/2 over d squared y dx squared. And we take the absolute value of the denominator because sometimes this value turns out to be a negative, but rho cannot be a negative, so it works to take the absolute value of that. This top term will never be negative because all those terms are always going to be positive. All right, let's talk about rho. How do we find the derivatives? Well, if y is equal to 1 over 100 x squared, dy dx is equal to 2 over 100 x, and d squared y dx squared is equal to 2 over 100. It's equal to 1 over 50. And this one can be evaluated at x equals 30. So when I plug 30 into there, that would be 60 over 100, which is equal to 0.6. All right, so now I plug those back into this equation, and I can discover that rho is equal to 1 plus 0.6 squared raised to the 3/2 over 1 over 50. And I get rho is equal to 79.3 meters. Now I can easily go back to my equation here and say A normal is equal to 25 squared over 79.3. That's equal to 7.88 meters per second squared. I had previously solved for A tangential, so let's go to our drawing and make sure we have our proper axes defined. So the roller coaster is moving in this direction, so this will be the tangential direction. The normal direction always points to the center of curvature, so the normal direction is positive there. I've got a tangential acceleration, positive, going in this direction. So it's going this way, A tangential. And this one is always going to point toward the middle at 7.88. A normal. And I can draw a little vector box here and say that this would be my total acceleration, A total right there. All right. So it's really important when we do these pictures or do these problems to, well, I guess I didn't calculate the total here. Maybe I should do that. A mag is going to be equal to the square root of 3 squared plus 7.88 squared, and that's equal to 8.433 meters per second squared. And that's the value that I drew in there. And back to what I was saying about the axes. It's really important to define the axes of the coordinate system as you go along. The tangential axis is going to go in the direction of motion. The normal axis, the positive normal axis, goes toward the center of the curve. All right. Well, I hope that helps get us started with the NT coordinate system.